Welcome. Today is April 19th, 2017, and this is the NARI Early Career Researcher Forum. This forum is intended to foster the exchange of ideas and be a platform where best practices for successful research are discussed. It is intended to highlight compelling research, build up the natural hazards engineering student community, and provide presentation opportunities. For more information, visit the NARI website at designsafe-ci.org, where you can find links to the SimCenter and NARI Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructures Simulation and Computational Modeling Center. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today's presentation is by Shanshan Wang, a PhD candidate at UC Berkeley. The title of her presentation is High Performance Computing Aided Optimization of Viscous Damped Steel Buildings to Achieve a Target Performance Goal. Before joining UC Berkeley, she was a student at the University of Tongji in China. And Shanshan, I'm going to turn it over to you at this time.
Okay, thanks Matt for introduction, and it's a great pleasure. And thanks SimCenter to provide me this opportunity to share what I have been up to at UC Berkeley. And of course, thanks for all your attendees for your interest and your time. And hopefully I could entertain you for the next hour and you could find something interesting and useful. So the topic today is about retrofitting an existing high-rise steel buildings using fluid viscous dampers. And the focus would be on using high-performance computers to streamline the design effort. I will start by talking about the background research first, and then more focused on how the optimization study is formulated for these engineering problems. And after that, I will share with you some of the experiences using high-performance computers in the design safe, and then the concluding remarks and the future works. So this work is embedded in the Tall Building Initiative project launched by the Pacific Earthquake Engineering Research Center more than a decade ago. And the phase one of the Tall Building Initiative focused on improving seismic performance of newly designed tall buildings and culminated in a series of guidelines as here. However, there are a lot of existing tall buildings all around the world, and many of them were constructed during a period when the understanding of seismic hazard and the structural analysis were not as advanced as now. So that seismic safety and resilience might be a problem. With that said, the second phase of Tall Building Initiative have expanded to examine the seismic performance of these existing tall buildings. And more importantly, if they do pose problems, we want to find some cost-effective ways to improve, to retrofit them and improve their performance. And to do that, we first selected one of the representative buildings from the candidate buildings. And one of the buildings we have examined in detail is a 35-story steel moment-resisting frame in San Francisco. And this building was finished construction in the early 1970s. And we generated in a numerical model in OpenSEES, 3-dimensional, and it was identified to have a fundamental period of about 4.7 seconds. And with this numerical model set up, we then relied on several referenced guidelines, including the AEC 14.1 seismic evaluation and retrofit of existing buildings, as well as several FEMA documents. And regardless of which document we use, there are several common seismic vulnerabilities that were identified associated with this building. Specifically, it has a significant trend to form weak stories and correspondingly have an unacceptable large number of beam-to-column connections fail at this most concentrated deformation zone. And also the columns pose a big problems in this building. It had widespread column stress fracture on the tension side, and also it is inadequate in compression. So in short, this building in its as-built condition would fail to meet the basic performance objective that would be recommended by AZ 41. Then the question is if we can find out some feasible ways to improve its performance. So we started looking at the different retrofit strategies, from most conventional ones to more novel ones. And with some efforts, we come up with a two-level retrofit plan. And in level 1 retrofit, we targeted at the most critical issues, including the fixed column splices, so to ensure the seismic integrity of this building under a major earthquake. And another retrofit measure we've taken in this level of retrofit is by replacing the heavy concrete cladding in the exterior of the building with some light curtain walls. So with such level of retrofit, the performance of the building actually improved a lot under a moderate earthquake, but further analysis result indicated it was not sufficient to maintain a limited safety performance goal under a major earthquake. So we needed to find some additional ways in order to augment such level of retrofit. In the level 2 retrofit, I mainly focused on using supplemental energy dissipating devices. And there are 3 devices that are examined, including the fluid viscous damper, the viscous wall damper in the middle, and also more traditional buckling restraint braces. And among these 3 I examined, the fluid viscous dampers has the most out-of-phase property and has the least interaction with existing structure members. And thereby it would turn to be the most promising solution in terms of improving the structure performance. And thereby I will talk about the design of the fluid viscous dampers in detail shortly. So while we're trying to figure out a design procedure scheme in an existing tall building, there are several factors we need to account for. And the first thing is which would be appropriate locations to locate these dampers. And first of all, it would depend on the functional and architectural constraints. So for example, this figure in this slide shows you a typical floor plan view of this building, and there are a lot of crossed box here indicating either the stairwalk or the opening. So it seems if we locating dampers in these interior frames, it will interfere a lot with the office space as well as egress, not only in the use phase, but also in the construction phase. Thereby, it seems that the exterior frames would be more appropriate to install these dampers. And in each phase of the frame that use dampers, the problem is which are the locations that would be more effective to have dampers. So to do that, I initially looked at the 3 different schemes in terms of how the dampers are distributed throughout the floors, and I distributed dampers at all the floors and compared the different 3 schemes. And the one scheme that sized dampers proportional to story stiffness turned to be the most efficient. Then next, based on the results from structural analysis as well as the damper forces, I used consistent criteria and trying to refine such a distribution pattern. And in these lower parts, where larger damping are required, the dampers are retained and increased in size. And once the story goes up, there are less damping required, so it's either removed or reduced in size. And also, we can notice these dampers are actually distributed from multiple base, that is to avoid the possible accumulation of damper forces to the columns that are connected to these dampers. So with that, we kind of have idea as well would be effective locations to install these dampers. But we still have a lot of things to consider here. And for example, we need to first estimate what's the total effective damping ratio needed to achieve our target performance. And to do that, I based on a criteria of the roof displacement, and to make sure that effective damping ratio could bring down the total roof displacement to a level that no abrupt reduction of the building strength would happen. And that result gives me about 10% damping in one direction and 15% in the other direction. And another parameter, the damping exponent, which designates the nonlinearity of these fluid viscous dampers, is also an important parameter. And I did some sensitivity check in terms of this parameter for this case study building. And it gives me a range of from 0.3 to 0.5, which could ensure the good control effect of these dampers. In the meanwhile, not inducing excessive large damper force. And another design parameter we couldn't neglect is about the stiffness of the spring that is in series with the damper. So in order to maximize the energy dissipation capacity of these dampers, we want most of the deformation to be concentrated in the dashboard. And in order to achieve this goal, we want the spring to be relatively stiff. And I did another sensitivity check, and it resulted that if this value is in the order of twice of frame stiffness, the full damper efficiency could be ensured. So I selected this value for the subsequent studies. And the last but not least is about the damping constant, which is perhaps the most important thing in terms of sizing these dampers. And this is a major parameter I selected for my study. So in the previous case, I showed you like how I refine the scheme based on this procedure, but it's on a manual design based. And this factor in the later optimization study I will show shortly is also selected to be the design parameter. So let's take a look how this proposed retrofit brings us. So in this slide, the left figure shows you the median structural responses for 3 different cases under the basic safety level 2 earthquake with a return period of 917 years. So the black line is a case without any retrofit, and the blue line is having level 1 retrofit. And it's clear that only after incorporating dampers could we fully get rid of the soft story and the drift concentration in story 5 to 10. And it brings about the peak maximum drift ratio to about 1.5% in mezzanine level. And following up on this structure analysis, we could continue to do loss and damage analysis based on the FEMA P58 methodology. And this histogram shows you the median total financial loss. As we can see, the case for the as-built condition as well as having level 1 retrofit, it has more than 15 chance to be replaced. And so the total financial loss is a combination of replacement cost and the business interruption loss. And after using dampers, we could avoid the replacement, and the total financial loss could be bring down to less than 15 million, say. So we can see under such level of earthquake, the savings from the loss would be more than 700. So on the other hand, if we estimate the retrofit investment, the damper price for this scheme is about 6 million. And if we consider any other factors to construct this retrofit scheme, and by time and multiply by a factor of 10 or 20, it's still a lot of incentives, and the cost benefit is clearly in for this proposed retrofit. So up to now, we have demonstrated the feasibility of using the proposed retrofit plan to improve the seismic performance of this existing building. And we can see the design procedure of dampers in this building mainly relied on the manual trial and errors. So that's kind of repetitive and labor intensive. And with that said, we want to explore some smarter ways and more efficient ways to achieve the same purpose. And that is motivation for the continued optimization study. So to do that, we needed to first formulate the optimization problem for the engineering problems I'm faced with. And there are several basic ingredients for the optimization study. And the first is to select the appropriate design variables for this study. And as I mentioned earlier, for designing dampers, there are several factors to be accounted for. For example, the locations and the different mechanical properties of these dampers. And all of these could be in the candidate pool to be the design variables. But in order to simplify the problem and control the number of design variables for these problems, I arbitrarily select the damping constant to be the design variable. And further, I mix some groups. Essentially, the dampers in the several continuous flows would be categorized into one group, and in each of these groups, the dampers would have an identical damping constant. And also, since for this building, the effective damping ratio required are different in two horizontal directions. So I used the different design parameters for the damping constant in each direction. So that gives us a total of 8 design variables. And these design variables are designating the damping constant at different levels. Their initial values as well as the range are selected based on effective damping ratio, a range when the damping would be reasonably provide a good control. And another ingredient in the optimization problem, which is probably more important, is about the objective function we want to use. So the focus is to improve the seismic performance. So the most straightforward objective function we could use is the engineering demand parameter. For example, in the previous cases, I looked at the maximum of peak drift ratio or the maximum peak flow acceleration, the two most important parameters that we would evaluate the performance of building and its damage status. And in the next stage, I also trying to look at functions that could, based on this engineering demand parameters, to inform the total building loss, which is termed as the engineering demand parameter decision variable functions. And these functions is kind of a simplified version of damage and loss analysis in the total performance-based earthquake engineering framework. So specifically based on previous loss and damage analysis for this building, we could generate a lot of data for the loss related to the engineering demand parameter for different performance groups. And the objective function would be a summation of these functions for different seismic sensitivity performance groups. And there's another factors we need to consider in the constraint and nonlinear optimization problem. And these constraints could be selected based on the performance goals you want to achieve. And in the problems I'm having now, since I use the maximum engineering demand parameter in the objective function, so in the constraint, I try to put a limit on the average structure responses. And in the meanwhile, I put a capping on the total maximum damper force as well as the maximum stroke in order to limit the damper sizes. So with the objective function, design variable, and the constraint defined, and we are ready to go. And we should keep in mind the objective optimization goal is to improve the structure response and also to satisfy the basic performance goal on the basic safety level 2 hazard event. And I also want to emphasize here, I use 11 records in this hazard in the structure analysis phase. And before I show you some results on the optimization part, let's first go through the procedure for the whole optimization flow. So to begin the optimization problem, we'll first set up initial values for all the design parameters you use, as well as to define some optimality criteria in the optimization engine, which will based on when the optimization will end. And with that, once that is set up, you would go into the one iteration, and then the optimization engine will try to evaluate the functions in the selected iteration point, as well as several adjacent points near the iteration point. And after several sets of such function evaluations, it could also estimate the gradient base for these functions, and it will select a most efficient direction to update the design and goes into another iteration point. Then the optimization engine will compare the objective function between two adjacent iterations. And if any of the optimality criteria is met, then the optimization will end. Otherwise, it will go into another loop. So as we can see, in this box showing you, in one iteration, it involves the function evaluation not only at this iteration point, but also at several adjacent points near that. And in each of such points, we need to evaluate such functions. And in each of such function evaluation, it involves the structure analysis for 11 times in my case, or for some more cases if you use more ground motion set. So as we can see, there are a lot of computation needed for the analysis, especially for a very complicated numerical model. So such a procedure might seem to be infeasible or prohibitively expensive to do in the past, but now we have a lot of resources to help us to go to the high-performance computers as well as parallel processors. So this problem is doable nowadays. And in my case, I use the Stampede system in the Texas Advanced Computing Center. All right, now let's take a look at how the optimization brings us. And in this study, I picked one case where I use the total building loss, the normalized ones, as objective function. And in the left figure, it shows you the propagation of how the optimization function is changing during different iterations. And there are several red dots here, shows you how improvement this objective function is making over the iterations. And the other points in the blue line are the adjacent points near each iteration. So as we can see, there is a very large improvement over the first iteration to the second iteration point. It brings down the objective function to, from more than 0.045 to about 0.202. But after the first update, the incremental increase would be limited. And then for the reasons I will discuss shortly. And in the red figure I'm showing you here, it shows you the design variables at 3 selected iteration points. So as we can see, in order to bring down the objective functions to have a nice design, we need to increase the damper sizes in both directions. But in the first update, we can see a large increase of damper size is happening in one direction. But in the subsequent 2 iterations, the optimization engine found it's more effective to increase damping in the other directions. So it made some modifications correspondingly. So this is about the overall view of the optimization process. Now let's take a look at the overall structural responses at the selected iteration points. So in this figure, I'm showing you the median response of the drift ratio for iteration points 1, 2, and 4. So clearly, in the first design, start with some damping that is relatively low, so there's still a large drift in the story from 5 to 10. And after the first update, the concentrated drift in this region is essentially eliminated, but the maximum drift goes to the mezzanine level. And I should point out here, in this building, in the mezzanine, it only has a slab on one side of the floor plane, so there's some vertical irregularity and a deficiency of the story stiffness, and which was not fully addressed. So that cannot become a bottleneck for the continued optimization. And after the second iteration, there's slight improvement afterwards until it hits the final design. And in the right figure, it's about the flow accelerations. So that is different from the drift ratio distributions. The improvement of the flow accelerations over different iterations is actually very limited. And on the other side, we could also take a look at how the dampers are behaving. And in this figure, I'm showing you the maximum damper forces that resulted from the structure analysis. As we can see, from the first iteration to the second iteration, there's a large increase of dampers to accommodate for the reduction of the drift. And the one thing I want to point out here is that in the final design, the damper sizes in the mezzanine level hit the 1500 kips, which is a limit I imposed on in the constraint. So with that said, we can see the optimization engine is working, and it could come to a better solution with very limited iterations. And another interesting thing is to see like how good it is compared to the scheme I proposed earlier, which based on the manual trial and errors. To compare whether the computer is doing good job or myself. So now let's take a look. So in this figure, again, I plot out some of the median structure responses from the structure analysis, and there are several cases I listed here. So the black dashed line indicates the case having only level 1 retrofit without the dampers. And also there's a gray dashed line, which is based on manual design. That is to say the design I come up myself. And the colored 3 lines are the automated design proposed by the computers. So clearly, in terms of drift ratio, the computers beat me, and it did a better job than myself, and it brings down the maximum drift ratio from my case 1.5 to about 1% in the mezzanine level. And in terms of the flow acceleration distributions, the manual design is actually slightly better in terms of bringing down the flow acceleration distributions. And the one thing we need to note here is that in the manual design, I use the dampers differently at every other floor. So that might provide more out of phase of each dampers in the floor, and might part of the reason why the manual design is doing a better job than the automated design. And again, we look at the damper forces. So for these damper forces, it doesn't seem to be a dramatic changes between different cases, either manual design or the automated cases. But the one thing I want to point out here is that in the manual cases, since I sized the dampers proportional to story stiffness, and in the mezzanine level, such a scheme was not sufficient to identify a damper sizes that is efficient, that is necessary to bring down the drift in this level. So it failed to end up with a good solution. So following up on these results, I extracted the maximum responses from before and summarized in this figure. So on one side, if we compare the case without using dampers and with the case using dampers, so clearly the dampers helped a lot to improve the structural response. Essentially, it eliminated the probability of the building being irreparable. And also it brings down the total median building losses from more than 740 million to about 14 to 20 million for different damper schemes. And on the other hand, if we make a comparison between the manual design as well as automated designs, so it seems that automated cases is doing a more efficient job here. It brings down the total building loss to about 14 and 6 million more than the manual case I proposed herein. But if we take a look at the damper prices for different schemes, there doesn't seem to be a significant changes, and the discrepancy would be much smaller in terms of the reduction of the total building loss. So, in shortly, the automated optimization works and is more efficient than manual case. And that probably is not the best part in terms of automatic design, because there are a lot of people much smarter than I do and more familiar with structure analysis and has more experience, probably will come up with some damper solutions that beat the computer. But one of the advantages we couldn't neglect is the time dedications for the manual design and the automated design. For example, in this case, in this table, I'm showing you the time dedications that needed for either manual design or automated design. And in the manual case, we first need to select the initial scheme to start with. As in my case, I started looking at the 3 different distribution patterns and trying to figure out one that is most appropriate for further design. So that might take you a week to come up with that initial design scheme. And with that, you need to run the structure analysis, and then after the structure analysis done, you need to extract the results and trying to do some post-process. And based on the results, you rely on some consistent evaluation procedure over the structure response as well as the damper forces, and trying to update the design. And that takes another week. And in total, it might take 3 weeks for per design, and it's likely that will requires more than 1 design for you to come up with a solution that you are happy with. So a total procedure for the manual scheme might take us about 2 or 3 months. But on the other hand, in the automated design scheme, the most effort comes into develop the automated tool. And that actually is kind of a straightforward procedure. That is to say, in most commercial softwares, like the MATLAB I'm using, it has some optimization package. So we don't need to worry about come up with optimization algorithm. And what we needed to do is to identify the design parameters, select objective function, constraint function, and trying to link the software that will run the structure analysis, and then collect the data back from the structure program and do the post-process and transfer the data back to the optimization engine. And that is kind of straightforward and not complicated coding required. And it might take you half a week to set all the problems up. And then next thing you need to do is to click the button and then let the optimization do the work. And after 3 to 5 days, you come up, the computers will give you a good enough design. And so in previous days, high-performance computers might not be available, so that might take a lot of efforts in order to do that. But now, the high-performance, there are a lot of resources to be accessible to a lot of researchers for free, and even if we need to buy it, it's not expensive at all. For example, for an on-demand hourly cost for 25 cents based on Amazon Cloud for 16 CPU computers. A 5-day computer time is equivalent to about $13. So that is a very good trade, is to say you trade $13 with 5 free days. I think that is pretty good, and I will vote for that at least. So with all that said, let me show you a little bit more about my experience using high-performance computers in the DesignSafe platform. So in order to use these high-performance computers, you need first to apply for the allocations from their user portal, and they provide the different types of these allocations. As for my case, I was granted with a startup allocation, which gives me 50,000 system units, which is enough for my case. So if you need more than that, you could write up a proposal and apply for the research allocation, which will give you 500,000 system units for you. And that is give you a quick flavor of how the user portal is like. You could always log into that and look at how much units you have been used so far. So have an understanding of where you are standing. And another thing is that once you get the allocation, you need to remotely control these supercomputers, and that could be accessed using a secure share. And the secure share is a network protocol that for operating network services securely over an unsecured network. So it will give you the channel to be logged into the supercomputers securely. And once you have been logged into their computers, you'll be placed on one of the 4 login nodes. And these nodes are actually the interface you deal with most, and which gives you the link to the back-end computer nodes. And the login nodes is where everything happens as a user. So we could do the pre-processing, editing, compiling files, or perform the file management or issue transfer and submit batch files. And once these jobs are submitted, it will wait in a queue and hand over to a scheduler manager, and the manager will allocate the resources available for you once it's your turn. And this is another screenshot from one of the secure share application I used. So you could log into your account using the secure share and locate the folders you want to run the analysis and upload all the files needed to run this analysis. So it's pretty straightforward. So in this slide, I would like to show you some of the tips in case you want to use the high-performance computers in the design safe. So first is about the secure share clients for Windows system. And this, like in my case, I use with Windows system, so I couldn't use the Linux command directly, but there are a lot of applications online that provide a secure share as well as Linux command, and they could be accessed for free. And in my case, I use the mobile XTerm, as I showed you earlier, which is pretty convenient and straightforward. And another suggestion is that try not to run programs on the login nodes. So the Stampede cluster is actually a shared resources. There are hundreds of users might log in, and hundreds of jobs are using the computer simultaneously. So you don't want to interfere a lot with others if you submit a job using language like this. So that would interfere with other users. So try not to do that and submit a batch file instead. And another thing is that you might try to not to run the jobs in the home directory. So the design safe provided 3 directories, and in my experience submitting jobs through the work and scratch folder would be much faster. But if you want to keep all your results, try to transfer these files to the home, which will provide you permanent access to store all these files. And another thing I noted is that not to submit simultaneous jobs at the same time. Otherwise, it will increase the number of times you need to wait in a line. And another thing I noticed that is the traffic is always much lighter during the weekend, so you might consider submitting jobs over the weekend, so it will reduce your waiting time for the jobs to be processed. And another suggestion is that you could try to monitor your files during the run if you are not comfortable to live through your 5 days without having a sense of how the working is standing. And that could be straightforwardly done by adding some comment and output some files. And you could use the cat command in the Linux system and try to see where you are standing in running the job. And in terms of the file transfer, you could use ACP or synchronized command there, and to upload your folders to the folders in the remote computers. But the most straightforward ways is always to directly drag the folders from your local computer to the folders in the remote computers. So anyway, these are some general tips. You can find more and more comprehensive information in the user guide in the Design Safe. And with that, I would like to conclude my talk. First, using fluid viscous dampers is a promising solution to upgrade the seismic performance of an existing steel buildings. And in terms of designing dampers, there are several parameters we could consider, such as the locations, the numbers, and the sizes. And this could be tuned manually, but it's not as efficient as it would be using an automated procedure. And now with the aid of high-performance computers as well as parallel processors, such a design effort could be streamlined, and the automated tool could efficiently identify the design parameters and gives us a good enough design, and which reduce substantially the computational time as well as human effort. And this is, so the study I'm showing you today is kind of some exemplar studies as how the high-performance computers could engage in our research work in earthquake engineering. And there are a lot of things we could do to refine such studies. For example, in the problems I'm dealing with, it could easily expand my problems by incorporating more design variables to make the case more general. For example, I could include the more damper locations as well as story-wise distributions, and also to increase the stiffness in the optimization as well to achieve some simultaneous optimization of damping and the stiffness. So that is one part, but there are other works we could do in the future, and which might also fit into the future scopes of what SimCenter will do in the future. For example, we could develop some tools to speed up such a procedure. Like in my case, I mostly relied on the MATLAB to do the optimization, which probably is not the most efficient optimization engine. And using some other open source optimization engine like Dakota could optimize could speed up such optimize the problems, and also to more efficiently use parallel processors. And also I think the SimCenter will trying to develop a more robust performance-based earthquake engineering engine. So with that said, we could make the things more streamlined and trying to do things more comprehensively. And the last comment I want to make is that now with the more computational capability and more information we will gather, for example, we could improve our understanding of the code procedures as well as gather more data from our modeling techniques as well as from earthquake engineer observations or health monitoring data. And with that, we could fully utilize the high performance computer capability and increase and set incorporating all this data in a platform, and in some day what we might need to do is just to click the button to run and let the computers to do the design, and it will give us a design that is general for most of cases and much better than ourselves would do, and so it will save a lot of us our roundabout time in the very beginning and very preliminary design. So with that said, we couldn't forget the most important part of this talk. So I would like to thank all my co-workers and Pierre who helped me all the way through from my PhD study, and as well as for a lot of professors and the engineers who provided consultations and shared their experience with me, which are very, very helpful. And a special thanks to Tim Cochran and Steve Marks from Design Safe, who generously provided me with all the resources to high performance computers, as well as patiently and efficiently address all my technical questions. And thank you so much. With that, I would like to conclude and would like to open the Q&A sessions. And By the way, this is my email address for those of you who haven't had a chance to raise questions in the next 10 minutes. You are always welcome to shoot me an email and to further our discussions here. Thank you so much. Is that our hand over to you?
For this informative presentation. On behalf of all of the participants, we appreciate your background and your knowledge and your sharing of this research with us. And so at this time, we're going to switch over to the question and answer session. We reserved about 10 minutes for this. The first question, there are several questions on the optimization and several questions on the modeling. So I'll start with some questions on the modeling. The first question is, does the optimization include level 1 retrofit, or is only level 2 retrofit considered in the optimization?
Yeah, sure. For my optimization problem, I started with the level 1 retrofit. So with that said, level 1 retrofit is incorporated in the optimization. I started with a baseline model that already fixed the most critical issues in the building. So to make sure the dampers would be most effective while we do the optimization.
Okay. And then regarding the modeling, there's a question about soil, and was soil modeled at all, and what soil properties were used?
Yes, thanks for bringing that up. Actually, the soil is not modeled in the 3-dimensional model, and we use a fixed based condition for this case study building.
Okay. Another question is the building numerical model fully deterministic in terms of mechanical and geometrical properties?
Yeah, that's right. So we based on like modeling some of the mechanical properties like the beam to column connections. These are based on the modeling parameters recommended by AEC 14.1. So essentially, like the post-yield capacity of these connections, they are estimated based on the size of the beams. So these are some deterministic numbers we put in the model. So the model is deterministic.
Okay. In terms of results, there's a question about the accelerations. Why are the accelerations not reduced during the optimization iterations?
Yeah, let's
go back to the slides for that.
So that's a good question. So I think one thing is that this one. Yeah, one thing is in the nature of such additional damping. So essentially, the added damping would be more effective to reduce the drift than it would be to reduce the total flow acceleration, and especially if you already have some level of dampings. And in this study, since optimization engine identified in order to reduce the total loss, the dampers need to be increased. So once you increase the damper sizes, the damper forces will be increased. That might end up with larger story-wise forces that will not help to reduce the flow accelerations. That's one thing. And another thing I would say in the optimization, I started with the design variable in the lower bound. So the optimization engine is not able to go in the other way, So it's not able to, the dampers might not be reduced. So the force of the acceleration couldn't go the other way. Yeah, hope that answers your question.
Okay. Maybe a follow-up question to that is what optimization algorithms were used?
So this optimization algorithm is based on a gradient-based algorithm, one of the algorithms available in the MATLAB optimization package.
Okay. If we go back to there's a question on column response, and the question is the column response improved after retrofitting?
Oh, great. Actually, I think I have a slides. After that, I have some slides prepared. So here we go. So in this slide, actually, that is showing you the maximum column actual demand to capacity ratios for different cases. And here in the positive sign designates the tension capacity, and the negative sign designates the compression capacity. So as we can see, the black line, which is the case without dampers, so it has more than half of floors having the demand capacity ratios 7.5, and after using different energy dissipation devices, they are not helping with the problem. And among the three cases, the fluid viscous sample seems to be the best. It slightly brings down the demand to capacity ratios in some of those, but it's not sufficient enough to bring down to a level that the colors might not be a problem anymore. And in the case of wall dampers, buckling with strained braces due to the additional stiffening effect, so the demand capacity ratio actually increases. So the answer is that these dampers will not help, didn't help with the column issues we face here.
Okay, and a few more questions on the optimization. We have time for just a couple more questions, and one is will the initial design variables change the optimal scheme?
Oh yeah, that's a very good question. So I think that probably depends. So for example, I tried to look at some cases in the very beginning where I only use the two design variables. That is to say, I arbitrarily select a design scheme, the damper distribution scheme of the stories, and just use one damping constant as a design parameter for each direction. So I end up having two design variables. And in that case, if I use different initial values, all this optimization will come to a stable point after several set of iterations. And so that for that case, the initial design might not be a big constraint or want to change the results dramatically. But in the case I'm facing, like as I increase the number of design variables, the results might change. Like in my case, I have 8 design variables, and it might end up with different solutions. And the one thing we need to note that since this is a very nonlinear problems, and the optimization problem is not a convex problem at all, and so there's no global minimum, and the optimization engine might have might find some local minimum adjacent to the initial design you start with. Yeah, so if you increase the design variables, it's likely you will have different final design, but hopefully all these different final designs would give you a decent design scheme and improve the structural response goal that we want to have. Yeah.
Okay. With the optimization, if you included additional variables, how do you expect the inclusion of other design variables would affect the time
the results.
The time use in terms of the high performance computing?
Yeah, I think that so my understanding is that it's done to increasing the number of design variables, not necessarily will increase the total iteration points. Like I showed you before, if you select some gradient that might work efficiently in your case, you might still have limited iterations needed. But the problem is that once you increase the design variables, you will increase the number of function evaluations adjacent to each iteration point. And this increase might be proportional to the number of design variables you are using. For example, if you want to use 100 design variables, and each of such function evaluation might the optimization engine might try to update the design variables one or a few at a time, and it would end up having more than 100 function evaluations at each iteration. So the computation time would be proportional roughly to the number of design variables you selected.
Okay. And 2 final questions about using the secure shell and design safe. One question is, what is the difference between using design safe and secure shell?
Oh, all right. Thanks for bringing that up. So I assume some people are already familiar with some design safe. So in order to use the high performance computer resources in the design safe, you have two alternatives. The first is to log into their website and to trying to utilize applications online. So what you need to do is to upload all the stuff in the computers in the website and then to submit the jobs through their portal. So it's similar to what it was be using in SecureShare, except that is done in probably one of the logging nodes instead of computing nodes. So it's not as efficient in terms of computing. And the one thing that using SecureShare is also much faster in terms of file transferring and do the actual computing, and you could also try more faster to submit your jobs. And another good thing about using the SecureShare over using their website directly is that it's easier for you to monitor. Like I mentioned, you could generate some files for you to monitor the process. Well, if you use the Design Safe website, you probably don't have the chance to see how the procedure is likely until it gives you the output files. And another good thing about using SecureShare, I would say, is that if using the SecureShare, you have the, I couldn't find it. You could also upload your own executable files. So you don't need for the technicians on Design Safe to upload all the executable files for the open source coding programs for your use. You could upload your own executable as long as it could compile to the Linux system. So that's another advantage over SecureShare and the Design Safe. Yeah. So I would vote for using SecureShare if you have such a chance.
Great. And are you familiar with what other software is available through the Secure Shell option for analysis?
Yeah, sure. The Design Safe, they actually provided some many applications, the open source code, as well as the commercial software like the MATLAB. But most of them are open source, like the OpenSEES, or the OpenSEES MP and SP and OpenForm, and also it has Jupyter. So these are all the executable files you could utilize in the Design Safe. Yeah, but yeah, there's a lot of variety of softwares we could utilize, and yeah, hopefully that answers your questions.
Great. So we're at the conclusion of today's Early Career Researcher Forum. Thank you to Shanshan Wang for her presentation titled High Performance Computing Aided Optimization of Viscous Damped Steel Buildings to Achieve a Target Performance Goal. And thank you for attending today's forum.